So hello everyone. So welcome to our this week Rutgers Efficient AI seminar. And today we are very honored to have the Professor Bing Ren from the College of William Mary to give us the talk on the machine learning compiler. Professor Ren is currently assistant professor in the Department of Computer Science at the William Mary College. His research interest lies in compilers, parallel computing, software systems, real-time machine learning, and machine learning systems. He has published over 50 peer-reviewed papers in leading conferences. He is the recipient of the NSF Career Award, the Jeffers Trust Award. His CGO 13 paper earned that Best Paper Award and was featured as a SIG-Plan research highlight and also nominated as the very prestigious communication of the ACM research highlight. He received the Best Paper Award and the Best Student Paper nomination in the Supercomputing Conference, and the first place in the design context of the ISFPED. He also holds multiple patents related to compiler techniques. He received his PhD from the Department of the Computer Science and Engineering from the Ohio State University. He was once the postdoc research associate in the High Performance Computing Group at Pacific Northwestern National Lab under the Department of Energy. So now let's welcome Professor Ren to give us this talk.
Yeah, thank you so much, Professor Yuan. Thank you so much for the introduction, and thank you so much for your invitation. And it's my great pleasure to be here. And good morning, everyone. Today, I'm going to present real-time DNN execution on mobile devices with compiler optimizations. So at first, let's look at some background information. As we all know nowadays, deep learning and deep neural networks are everywhere. And many real-world applications require the deep learning and deep neural network capabilities, like self-driving, speech recognition, object detection, and we also need them in the gaming scenario and also the healthcare applications. And we have the deep neural networks and deep learning applications running on various kinds of hardwares, including the different kinds of GPUs and FPGAs and Google TPUs on both the edge side and also the server, the cloud side. And of course, we have different kinds of NPUs. Our research actually focuses on the running deep neural networks on mobile devices. This is because of three major reasons. The first reason is because of the latency. Assume if we run a DNN model on the server, actually the data transfer between the server and the mobile devices takes time. Yeah. This is because of the latency reason. And the second one is because of the privacy. Sometimes the users don't want to run their, don't want to upload their data to the server. They want to run the AI capability locally and to protect their privacy. And this is the second reason. And the third reason is actually because of cost. Usually the vendors also want to run the AI capability on the mobile devices, because if they run this kind of capability on the server, they need to pay for it. So if they want to save this kind of cost, they also prefer to run AI capability on the mobile side. These days, different kinds of mobile devices become increasingly powerful. Let's look at an example here. This is a Snapdragon 888. It consists of CPU, GPU, DSP, and NPU. So it's very powerful. However, it's still challenging to run large DNNs on a mobile device in real time. This is because large DNNs are very computation intensive and memory intensive. Take VGG 16 as an example. If you want to inference one frame, it usually takes around 100 milliseconds to 200 milliseconds with the cutting edge DNN execution frameworks. However, the real-time requirement is 33 milliseconds per second. So per frame. So you can see there is a huge gap between the the real-time execution and what we can get these days. So how to fill this gap? How to, run the deep neural networks on the mobile devices in real time? This is a important issue these days. And there are many efforts targeting this kind of issue. And in this talk, I would like to introduce two solutions from our group. The first solution is called PET-DNN, and the second solution is called DNN fusion. PET-DNN actually is a kind of compression and compilation co-design, which is published in S+ 2020. And DNN fusion actually is a kind of operator fusion technique, which is published in PLDI 2021. Let's look at PET-DNN at first. At first, let's look at more background information. As we mentioned, there are many efforts targeting improving the DNN execution performance on mobile devices. Especially, we can categorize them into two fields. In the algorithm fields, for example, in the algorithm fields, and there are lots of DNN model compression techniques. In this talk, we focus on the weight pruning technique. And we also have other kinds of techniques like model quantization, but that is not covered by this talk. And there are also many efforts from the system field. People design different kinds of mobile platform acceleration frameworks to accelerate the execution of deep neural networks like TVM, TensorFlow Lite, and Alibaba MN. All of these are highly optimized DNN execution frameworks. Of course, we have other efforts in the hardware field, like some new hardware design, some NPU, TPU design, and but that is beyond the scope of this talk. We don't cover this kind of part in this talk. Actually, if we take a look at the existing pruning approaches, actually we can categorize them into two groups. The first one is non-structural pruning, and the second one is structural pruning. The non-structural pruning, in the non-structural pruning, actually we prune the model in a random way. So we can prune any weights as we need. And the advantage of this method is we can enjoy the pruning flexibility, and we can achieve high pruning accuracy, and also the high pruning compression rate. And the disadvantage is the resulting model is super irregular. And as you all know, the modern hardware doesn't like this kind of irregular computations. So this is about the non-structural pruning. And about the structural pruning, the advantage is, because in the structural pruning, we are going to prune the entire channel or the entire filter. And so, the resulting model is very regular. So it's very hardware friendly. We can achieve good execution performance. However, because we need to prune the entire filter of the channel, so usually, we cannot enjoy the pruning flexibility. So usually we can have we will have a low compression rate, and also the resulting model accuracy will be degraded. So this is limitations of existing pruning approaches. And let's look at the popular frameworks like MNN, TVM, and TensorFlow Lite. As I mentioned, all of these are highly optimized frameworks to execute DNN applications. However, they cannot support real-time execution of DNN models on mobile, because mainly because they cannot efficiently support compressed models on mobile devices in an efficient way. So so this is a major limitation of the existing popular frameworks. We are going to have some performance comparison between our work and these popular frameworks. And based on this information within this kind of context, let's introduce our contributions. Actually, we have three kinds of contributions in this PET-DNN work. And the first contribution is we design a fine-grained structural pruning, which is called pattern-based pruning, then that can preserve both the high regularity and high model accuracy. High regularity means we can achieve good execution performance. So this kind of pruning can achieve both high execution performance and high model accuracy. And the second one is, we based on this fine-grained structure pruning, actually we design an end-to-end framework. We call it PyDNN to efficiently execute DNN models on mobile devices. And especially in this end-to-end framework, we have a set of compiler-based optimizations. These compiler-based optimizations can transfer the pruning, the computation reduction into real performance gains. And then at last, we compare PyDNN with 3 state-of-art end-to-end frameworks. They are TensorFlow Lite, TVM, and MNN. And we show PyDNN outperform all of these frameworks. So let's look at the designs in the PyDNN one by one. First, let's look at the basic idea of the pattern-based pruning. And the idea is pretty straightforward. When we prune the kernels, actually, we need to follow certain patterns. For example, here we have 3 by 3 kernel. And when we prune this kernel, we just follow certain patterns like this. We leave 4, we preserve 4 non-zero weights for each kernel. And if we take a closer look at this approach, actually, this approach includes two methods or 2 sub-approaches. The first one is called kernel pattern pruning, which is taken on each kernel. So when we prune this kernel, we just follow a certain pattern. And the second one actually is, the second sub-approach is to prune the entire kernel. So which is equivalent to cut the connectivity between certain input and output channels. So we call it connectivity pruning. So this approach has these 2 levels of pruning sub-approaches. One is kernel pattern pruning, and another one is connectivity pruning. Actually, this figure summarizes this pattern-based pruning approach. And first, we have the pre-trained model and also a set of predefined patterns. And then we are going to use the ADMM approach. Actually, it's an enhanced ADMM approach together with this predefined pattern set to select the patterns for each kernel. After that, we are going to retrain this model. We are going to fine-tune this model. And then we get the pruned model with both the good accuracy and good comparison ratio and good computation regularity. So if you would like to learn more information about this approach, especially what's the theoretical foundation of this approach and what's the exact step of this approach, please refer to this IEEE 2020 paper. And in this talk, I'm going to focus on the system aspect of this product. And let's look at a system overview here. And at first, we are going to have a pattern-based pruning. We are going to prune the models and into a pattern-based pruning model. And then this pruned model will be converted into a computational graph. And then we are going to perform different kinds of graph optimizations on this computational graph. These are existing efforts. So this is not our major contribution. Our major contribution is here. So after we get the computational graph, actually we can design a layer-wise representation for each layer of this computational graph, particularly for the convolutional layers. For example, this is an example of layer-wise representation for a layer in VGG 16 model. In this layer-wise representation, we will represent the pattern information. For example, what's the pattern ID of this layer and what's the storage of this layer. And also we include some information which is not related to the pattern. For example, some general tuning parameters like the unrolling factors, tiling factors, and what kinds of permutation we are using, and also some basic information about this layer. For example, the stride and the dilations and other information. So this is a layer-wise representation. Based on this layer-wise representation, we are going to do we design multiple compiler-based optimizations. The first one is called filter kernel reorder, and the second one is called load redundancy elimination, and the third one is parameter tuning. And after this, we are going to generate both the compact model and also the optimized CPU and GPU code. And in this talk, I'm going to especially focus on the filter kernel reorder, load redundancy elimination, and the compact, model storage. Okay, so let's look at them one by one. First, let's look at the filter kernel reorder. In this figure, we show a layer of a DNN. Each cell represents a kernel, and each row actually represents a filter. A filter has multiple kernels, and on each kernel we have a number, and this number denotes the pattern ID of this kernel. And this empty kernels means we prune this kernel completely by the connectivity pruning. So after this after our pattern-based pruning, we are going to get the model looks like this. Yeah. And then we are going to perform the reorder operations. The first reorder is a filter level reorder. We are going to reorder the filters. The metric here is, we need to organize the filters with the largest similarities together. Okay, for example, this filter and this filter share the most similarities. So we are going to organize them together. And this filter and this filter share the most similarities in terms of the length and the pattern. So we are going to organize them together and so on. So this is called filter level reorder. After this filter level reorder, we are going to perform a kernel level reorder. We are going to reorder the kernels based on their ID. So we are going to, for example, we are going to, for the first filter, we are going to put the kernel with pattern ID 1 at first, and then the pattern ID 2. And after that, we can partition these filters into multiple groups. And in this example, we have limited number of filters in each group. However, in the real deep neural networks, we have lots of much more filters in each group. And then we can assign each group to multi-threads. We can execute these filters concurrently. So this is a basic idea. And after this filter kernel reorder, when we do the parallel execution, actually the threads can share similar workload. So we can improve the load balance, and also we can improve the thread level parallelism. And in addition, actually, we can also improve the instruction level parallelism. For example, if we take a closer look at the code, this is the code before the filter kernel reorder, and this is the code after the filter kernel reorder. In the left code, actually, we can see, actually, we have the switch statement here. This switch means we have lots of branch operations. And however, on the right hand side, after the filter kernel reorder, we don't have any branches. Okay, we are going to go through each pattern one after another. So we totally get rid of these branch operations. So the branch operations actually hurt the instruction level parallelism. So after the filter kernel reorder, we can get better instruction level parallelism. So this is about the filter kernel reorder. After the filter kernel reorder, actually we can also store the model in a more compact way. So if you take a look at this example again, then this is reordered kernels, and actually we can store these kernels in a more compact way. And we can store all the kernel weights next to each other by a dense array, and then we can create multiple level index for this dense array. So if you are familiar with a well-known CSR format for the sparse matrix storage, then probably you will know actually we have a dense array for the data. We have multiple level of index arrays to index this data. Comparing to this well-known CSR format, actually we leverage the pattern information. We further compact the index part. And after our, compact storage, actually we can save the index storage space by around 90% memory space. And in terms of the overall storage space, we can save around 40% overall storage space. So this is the advantage of this compact pattern-based model storage. And if you are interested in more details about this format, please refer to our paper. We have a detailed explanation about this, about the meaning of each index. And next, let's look at the load redundancy elimination. Actually, we have two levels of load redundancy elimination. The first level is a kernel level, and the second level is a filter level. In the kernel level, actually, let's look at this figure. And in this part, actually, each 3x3 picture actually is a kernel, is a 3x3 kernel, and each cell now is a weight. It's not a kernel. Each cell is a weight. So here, for the first kernel, we have two weights, which is 1 and 2. And weight 1 will require, if we do a convolution operation, weight 1 will require the first row, the data in the first row, and weight 2 will require the data in the second row. And then, we are going to, because it's a convolution operation, and in next round, weight 1 will require the data in the second row, and weight 2 will require the data in the third row. Then we can see actually the data in the second row are reused. Yeah, so it's reused by this computation and this computation. So in fact, actually we can load this data into the SIMD register, and then we preserve this SIMD register and we reuse for this computation. So this is an opportunity for the load redundancy elimination. So instead of loading this data twice, we only load this data once into the SIMD register. So this is the basic idea. And this is kernel level load redundancy elimination. And similarly, we can also explore the filter level load redundancy elimination opportunities. For example, if two filters have identical patterns. So for example, in this filter, we have two weights, 1, 2. Here we have 2, 1, but they have the same pattern. And then we are going to, we can reorder these filters, and we can do this computation simultaneously. And then they will require the same data, the first row and the second row of the input feature map here. And then actually we can load this data into the SIMD register only once instead of twice. So by this way, we can also reduce the memory load, especially from the cache to the register. So this kind of opportunity, actually, it's relatively easy to find in a dense model. So it's relatively easier for us to explore such kind of opportunities in the dense model. However, in the sparse model, it's not easy to find such kind of opportunities. And we can do this because of the pattern-based pruning, because we have certain patterns. And this pattern information will help us to explore such kind of load redundancy elimination opportunities. And another important issue here is because we are working on static model, so the model structure is known in advance. So we can actually generate the code for each kernel to explore such kind of load redundancy elimination opportunity. So this is the basic idea of this load redundancy elimination. So yeah, so we have introduced the major designs in PyDNN. Let's look at the evaluation results. In order to evaluate PyDNN, we compare it with 3 frameworks, which are TVM, TensorFlow Lite, and Alibaba MNN. All of these are highly optimized DNN execution frameworks. And we evaluate on multiple mobile platforms, including Snapdragon 855 and Snapdragon 845 and Kirin 980. And the second and third mobile platforms are used for the portability evaluation. Due to the time limitation of our talk, I'm not going to cover this part. Let's focus on the first one, the results on the Snapdragon 855. We use 2 data sets here. One is ImageNet, another one is CIFAR10. And also we use 3 networks, VGG16, ResNet 50, and MobileNet v2. And we evaluate on both mobile CPU and mobile GPU. And at first, let's look at a very interesting result about the relationship between the speed and the accuracy in terms of the pattern count. In other words, we are going to study the impact of the pattern count on both the execution speed and accuracy. So if we select, less patterns, for example, if we for VGG16, if we select 6 patterns, which means we have fewer patterns, we have better computation regularity. So we are going to achieve better performance, execution performance. However, we are going to sacrifice some accuracy because we have fewer patterns. So we don't have a full pruning flexibility. However, if we have more patterns, for example, if we have 12 patterns, we double the pattern count, then we can have a good accuracy. However, we are going to sacrifice the execution latency. So this is a trade-off. And in order to achieve the good accuracy and also the good execution performance, we need to select a proper number of the patterns. For VGG16 in PyDNN, actually we select 8 patterns, and with these 8 patterns, we can achieve the best combination of accuracy and also the execution performance. So this is the first evaluation. And let's look at the next evaluation. In this evaluation, actually, we show the overall performance, execution performance on both CPU and GPU. We also show the results on 2 data sets. One is ImageNet, another one is CVAR10. And A shows the results on the ImageNet CPU, and B shows the result on the CVAR10 CPU, and C shows the results on ImageNet GPU, and D shows the results on CVAR10 GPU. And the x-axis shows 3 different kinds of models, and the y-axis shows execution time. We compare our PyDNN with 3 other frameworks, TensorFlow-Lite, TVM, and MNN. If we look at the results on ImageNet A and C, and then we can see on mobile CPU, actually we can achieve up to 15 times speed up if we comparing the PyDNN with the TensorFlow-Lite on VGG. And on mobile GPU for ImageNet dataset, actually we can achieve 9 times speed up if we compare the PyDNN with the TVM. So this is a result. Actually, this result is evaluated, is tested. In 2020 and a few years ago, because when we do this project, and nowadays I believe TensorFlow-Lite and MN and TVM have improved their performance. However, there is still an obvious and significant gap between our performance and TensorFlow-Lite and TVM and MN. We can see, PyDNN is still faster than all of these frameworks. Let's look at, more details about the optimizations in PyDNN. Especially, let's look at the impact of these optimizations on the performance. So in this figure, actually, we show, we do a breakdown study on multiple layers of VGG16, and the y-axis actually shows different kinds of layers, and the x-axis shows speed up over the non-optimized version, and the first white bar shows the non-optimized version, which is normalized as 1, and the others shows impact of different kinds of optimizations, and the higher the better this result. And we can see, comparing with the reorder optimization, we can achieve a good performance, and with the reorder plus low redundancy elimination, we can achieve the additional performance gains, and with the tuning, and we can also see the additional performance gains. If we take a closer look at it, we can see on the mobile CPU, actually the low redundancy elimination contributes more than others. This is because CPU has limited number of registers, and the low redundancy elimination can improve the utilization of the registers. So that's why the low redundancy elimination impacts the CPU performance more. And if you take a look at the GPU result, we can see actually the reorder contributes more to the mobile GPU. This is because the GPU has multiple threads, and the thread level parallelism is more important. And the reorder helps the thread level parallelism, the low redundancy, and the computation regularity. So that's why the reorder contributes more to the performance of mobile GPU. Okay, so this is our first work, PET DNN. Actually, if you are familiar with DNN optimizations, probably you are going to ask one question like this. So PET DNN requires, model modification. It requires a model pruning, model compression, and also the retraining. So it's a little bit, it's a kind of, intrusive method. So we need to change the model. For many cases, people don't want to change the model because of different kinds of reasons. Yeah. So probably you ask, is there any method to achieve the good execution performance, but still not changing the model? So it's possible. This is our second work, which is DNN fusion. In DNN fusion, actually, we leverage a pure compiler technique to optimize the computational graph by advanced operator fusion technique. So, first, let's look at some background information. As we all know, nowadays, DNN becomes increasingly deeper. And this is because of the accuracy, consideration. If we increase the number of the layers of DNNs, then we can improve the accuracy. So for example, mobile BERT, GPT-2, conformer, all of these models have over 1,000 operators. Then what's the disadvantage of this kind of design? So actually there are two obvious problems. The first one is if we have too many layers, then we are going to have lots of intermediate results. We need to read and write these intermediate results, which will result in poor memory performance. And the second one actually is when we design the model, when we increase the number of the layers, we still want to maintain a reasonable workload for this model. So each operator in this model will become smaller. Then we are going to have insufficient parallelism for each operator. So these two challenges actually create problems for the performance optimizations. Let's look at some concrete numbers. And here we show the results for 5 models. And the first column actually shows the model names. And the second column shows the number of the layers. And the third column shows the number of the flops. And the last column shows, the inference speed. So, if we take a look at these numbers, we can find, okay, VGG16 has the least number of layers, and GPT-2 has the most number of the layers. However, if you compare the performance, the inference speed, then you can see VGG16 has the best inference speed, and actually this mobile BERT has the least inference speed. Particularly if we compare these two, VGG16 and Distill BERT, their overall computations are very similar to each other. One is 31, one is 35.3. Yeah, and however, if you compare their inference speed, and the VGG16 is much faster than Distill BERT. So actually, this gives us some hint. So at first, this proves our claims. Yeah. So as we increase the number of the layers, then the inference speed will be degraded significantly. And also, this gives us some hint. So is it possible to fuse some layers? Yeah, if you are familiar with DNN optimizations, probably you are going to ask this question. So is it possible to fuse some layers together? So the question is, of course, we can't do that. Actually, in this result, we have already used operator fusion technique, which is called fixed pattern fusion. And this technique is also widely used in TensorFlow Lite and TVM and MN. These very famous, DNN execution frameworks on mobile devices. The basic idea of this approach is we are going to predefine some fixed fusion patterns. And then when we optimize the computational graph, we are going to match these patterns with the computational graph. Apparently, this kind of method doesn't work well. Yeah. So, it cannot give us the optimal performance. And what's the reason? Actually, the reason is nowadays we have too many operators. If we consider ONNX, ONNX has over 100 kinds of operators. And if we consider the combinations of these operators, we have even more. So it's very difficult to predefine these fixed patterns to cover all of these combinations. So this is a critical issue in the operator fusion optimization. Then, our work actually targets this problem. Particularly, we answer these two questions. The first question is, which operators can be fused in the DNN? And the second question is how to perform an operator fusion after we find which operators can be fused. So to answer the first question, actually, we design a high-level abstraction of operators according to their input and output mapping. We call it operator mapping type analysis. This is a higher level than the operators, and it's more general. And it covers different kinds of operators, and also it can cover the incoming new operators. So we are studying essentially we are studying the fusion opportunities in a higher level, from a more general level. So this is a basic idea of the major idea of this DNN fusion technique. And after this, we answer the second question, how to perform the operator fusion. In this part, actually, we have three techniques. One is called mathematic property-based graph rewriting. With this rewriting technique, we are going to optimize the computational graph structures to facilitate the operator fusion. And the second, in the second step, we design heuristic fusion plan exploration technique to control the fusion cost. And in the last step, we are going to generate the fuse code by a recursive method. So let's look at these techniques one by one. Particularly, let's look at how to answer the first question. And we use the operator mapping type to answer the first question. And actually, we design multiple operator mapping types. They are which are one-to-one, one-to-many, many-to-many, reorganize and shuffle. For example, add and remove belong to the first one-to-one mapping type, and gather and upsample belong to the second one. Convolution and GMM belong to the third many-to-many. So what's the meaning here? Let's look at two concrete examples. I hope by these examples I can give you more concrete feeling about the meaning of these operator mapping types. So the first one is one-to-one mapping. And for example, here, this is addition operator. You can treat it as a vector addition or matrix addition, it doesn't matter. So the one-to-one actually means, for each input, each element, for example, input one, each element in this input one only contributes to one, result in the output. And it only contributes to one, and only one elements in input one contribute to the output as well. So you can see there is a one-to-one mapping relationship between this input and the output. So that's why we call this is a one-to-one mapping. However, if you take a look at this many-to-many mapping, then you can see actually many elements in the input contributes to one element in the output. And one input element can also contribute to multiple elements in the output. So there is a many-to-many mapping between the input and the output. So that's why we call this is many-to-many. So for example, convolution is a many-to-many mapping type. Okay, our next question is, after we find this, then which operators can be fused together? Yeah, we need to have some policies to specify which mapping types can be fused, which cannot. So actually, this table shows the most critical idea of this work. And actually, the first column shows the mapping type of the first operator, and the first row shows the mapping type of the second operator. And in the middle, we have many cells. And in each cell, we show the mapping type of the resulted operator. For example, for this cell, for this one-to-one, and which means if we fuse a one-to-one operator with another one-to-one operator, we are going to get an operator. For this operator, the mapping type is still one-to-one. So for this one, if we fuse a one-to-one operator with a one-to-many operator, we get a operator which is in one-to-many mapping type, and so on. So you can see, if we fuse a one-to-one operator with any other operators, then we are going to get a fused operator which is in the mapping type of the second operator. Yeah. So here in this part, we also color each cell. Yeah, we also color each cell. For example, we have the green colors, we have the yellow color, we have the red color. And the green cells means, for these cases, actually, this kind of fusion is both legal and also profitable. Which, for example, it's legal to fuse a one-to-one with a one-to-one, we got a one-to-one. It's legal to fuse a one-to-many with a one-to-one, we got a one-to-many, and so on. So this kind of fusion is both legal and profitable. And we can do this, without any further analysis. The compiler can do this kind of fusion automatically. And the second one actually is the green cases. The yellow cases. The yellow cases means such kind of fusion is legal. However, we are not sure if this kind of fusion is profitable. We need to use some further profiling approach to find if that kind of fusion approach is profitable. Okay. Of course, we can store the profiling result if we have into a database, and in the future, if we have any similar cases, we can just look up this database, yeah, to speed up this kind of profiling procedure. Actually, the red cases, these two red cases means this kind of fusion is very complicated. The compiler cannot easily figure it out. So the compiler will not do this kind of fusion automatically. Okay, so if we can do this manually, it's possible. Yeah, it's possible. However, it's very difficult for the compiler to figure them out automatically. So that's why we mark them as red, and we are not going to do this kind of fusion by the compiler automatically. Here we have two more examples. For example, we fuse a many-to-many operator with a one-to-one operator. We get a many-to-many operator here. And here we fuse a one-to-one operator with a one-to-one operator. We get a one-to-one operator. Okay, so this is the first technique, the operator mapping type analysis. And based on this analysis, we are going to perform the real operator fusion. And here we have three techniques. The first technique is called graph rewriting. The basic idea of the graph rewriting is straightforward. We are going to rewrite the graph to simplify the graph and to facilitate the subsequent graph operator fusion. So for example, before the graph rewriting, we have more complicated graph, and after that we have a simplified graph. And this it's easier to perform the operator fusion on the second graph than the first one. So we have some questions here that in order to do the graph rewriting, we need to define some graph rewriting rules. And how to define these graph rewriting rules? Actually, we define these graph rewriting rules based on the mathematical properties of these operators. Especially, we explore three mathematical properties, which are associative property, distributive property, and communicative property. And here we show some examples. These three equations are actually some commutative graphs and before the rewriting, and this part shows a subgraph after the rewriting. And we can see before the rewriting, actually we have more number of flops. In other words, we have more number of commutations. After the rewriting, we have less number of flops. We have less commutations. And also the structure, the equation becomes much easier, yeah, than the first one. So this kind of graph rewriting can facilitate subsequent operator fusion. Actually, we design, around 30 to 50 graph rewriting rules for each category, and in total we have around 150 graph rewriting rules to perform the graph rewriting. And if we perform the graph rewriting, for example, if we match all of these graph rewriting rules on the entire computational graph, this is very time consuming. It's almost impossible. In order to reduce the cost, actually we partition the computational graph by the point, by the operators which do not have any of these properties, and then we can match these graph rewriting rules within each sub-computational graph. This can significantly reduce the cost. So this is the first technique. And the second technique actually is a heuristic fusion plan exploration. And it's easy to prove. Actually generating a global optimal fusion plan is an NP-complete problem. So in order to control the cost, actually we design a heuristic method. In this heuristic method, we need to answer two specific questions. The first question is, which operator shall we fuse first? So which operator we should start our fusion? And the second question is, how to decide the fusion order? So to answer the first question, actually we are going to use the insight from the previous part. And I'm not sure if you still remember in the fusion, in the mapping type analysis, we have a very obvious phenomenon. If we fuse any one-to-one operator with any other operators, it's always legal and profitable. Yeah. So that then we can always start from one-to-one operators, because this can enable more operator fusion opportunities. So we call the one-to-one operators as seed operators, and we always start from these seed operators to perform the operator fusion. And we perform the operator fusion along two directions. The first direction is to head to the successor, and we are going to, for example, for this example, we have the add and convolution. We found add is one-to-one and the convolution is many-to-many. We can fuse them, and the resulted operator is many-to-many. And all the rest operators are actually one-to-one operators. Then we can continue performing this operator fusion. So we are going to generate many-to-many fused operator after this kind of operator fusion, and then we are going to head to the predecessors. And because DMM is also a many-to-many operator, and it's illegal to fuse a many-to-many operator with another many-to-many operator, so we are going to stop. So after this fusion plan generation, actually for this example, we are going to generate two subgraphs. One subgraph has only one DMM node, and another subgraph has five operators. In this step, we do not perform the fusion code generation. We are going to perform the fusion code generation in this step, in next step, and in the code generation step. In this step, we are going to, for each subgraph in the fusion plan, we are going to fuse them into a fused operator. In order to fuse it into a fused operator, actually we are going to extend the computational graph into an extended computational graph by labeling the data, intermediate data and output data on this computational graph, and then we are going to create a data flow tree. The leaf node of the root node of this data flow tree actually is the output of this subgraph, and the internal nodes are the intermediate results, and the leaf nodes are actually the input data of this computational graph. And then we can follow this data flow tree to generate the fusion code. We can follow, for example, in this example, we are going to follow its left subtree at first to fuse the left part of this computational graph, and then follow the right subtrees to fuse the right part of this extended computational graph. And at the end, we are going to generate one fused operator. So this is the basic idea here. Okay, so at the end, let's look at some evaluation result. And we evaluate DNN fusion by comparing it with, multiple DNN execution frameworks like MNN, TVM, TensorFlow Lite, PyTorch Mobile, and also we have our baseline version. And we evaluate our work on Samsung Galaxy, S20, actually, which is Snapdragon 865. And we evaluate on 15 models, including 5 2D CNN model and 2 3D CNN model and 2 RCN model and 6 transformers. Okay, so all of these are cutting edge, large DNN models. Then let's look at the fusion rate at first. And the fusion rate means, after this fusion, how many operators or how many layers we are going to generate. Okay, so if we take a look at this table, we can see actually the left part actually shows the layers or operators before the fusion, and the right part actually shows layers or the operators after the fusion. These are the results after the MNN fusion, and these are the results after the DNN fusion. And then actually let's look at this. If we compare this result, actually we can see DNN fusion can result in up to 8.8 times better fusion rate, which means we generate more, fewer fuse operators, and each operator will be larger. Yeah. So in this kind of case, we can significantly reduce the intermediate results and also improve the parallelism of each operator. Particularly if we compare these two models, we can see for larger models, actually our fusion rate is better. Yeah, is better. Okay, then let's look at the inference latency. Yeah. So the left part shows the inference latency of different kinds of frameworks, and our B actually is a version of our baseline version. In this baseline version, we do not use any fusion technique, and our B plus actually shows the performance with a fixed pattern based fusion and our baseline. Yeah. In other words, we integrate the fixed pattern based fusion with our baseline, and then we get this version. And then the DNN fusion actually is with our advanced operator fusion technique and our baseline, we got this inference latency results. So if we take a look at this result, we can see comparing to existing frameworks, we can achieve up to 9.3 times speed up. And particularly if we take a look at our B, our B version, it's already faster than other frameworks. And our advanced operator fusion can bring extra gains. So let's look at some evaluation result on the, let's do some application study or breakdown study here, and to analyze the effect of different kinds of DNN fusion optimization techniques. So again, the x-axis shows different kinds of models, and the y-axis shows the normalized speed up, and the higher the better. And we normalize the performance by the RB version, and the second bar actually shows performance with the graph rewriting, and the third bar actually shows the performance with both the graph rewriting and the fusion. And the next bar shows with the graph rewriting, fusion, and other techniques like the tuning and other optimizations. And the last bar actually is very interesting. It shows performance with only fusion and other techniques without graph rewriting. Okay, so from this result, we show both the CPU result and GPU result here. And from these results, actually we can see actually fusion, operator fusion contributes the most to the performance gains. And particularly if you compare the red bar here with other bars. Yeah. And more importantly, if you compare the blue bar and the yellow and the orange bar here, then you can find a very interesting phenomena. If we do not have the graph rewriting, even we have the fusion, but we still cannot get the ideal performance. This is because graph rewriting not only improve the computational graph by reducing the computation, but also enable many new operator fusion opportunities. Okay, So actually, the last two parts shows the advance of our graph rewriting technique. All right, at the end, let me show some interesting demos. We have some super resolution demo. The upper window shows a low resolution video, and the lower window shows a high resolution video. And this version is relatively older, and nowadays we can achieve around 30 to 40 frames per second. So which is real time or ultra real time. And the second one is graph graph coloring, and the third one is style transfer. We can transfer this video into a Pepper Big style. And then we have the activity recognition. And for this one, actually, we can also achieve ultra real-time execution. And this one is a famous object detection model, YOLO. And we can put it onto a cell phone device, and also we can achieve real-time execution. So thank you so much for your attention. Actually, my research belongs to actually serve as a research foundation for a larger project, which is called CocoaPi, and this is an ongoing project. It's a collaborative project among Northeastern University, North Carolina State University, Perceptin, and William and Mary. So if you are interested in this project, please refer to our YouTube and Bilibili channels. Yeah, we have more interesting talks and demos. So thank you so much for your attention. If you have any questions, let's have a discussion here. Thank you so much.
Thank you, Wim, for very informative talk. Yeah. Actually, I have several questions, but I would like the audience to ask first.
Sure. Yeah.
And any questions from the audience? You are free to unmute yourself. I think I can ask some questions first. Sure. Yeah, so my first question is that, so in your evaluation table, so you listed the results on many state-of-art models. So I was wondering, so do you have ever tried your method on the emerging vision transformer?
Yeah, this is a great question. Yeah, this is ongoing work. Yeah, ongoing work. In the vision transformer, actually, it shows some dynamic features, very interesting dynamic features. We are going to this kind of techniques can be applied to the dynamic vision transformer, and for example, for the operator fusions. But we need to improve it. Yeah, we need to consider some dynamic features of this kind of models. So yeah, this is ongoing work. Yeah, we are working on this.
So you mean that there's some unique challenge and opportunities when you apply this method to the vision transformer?
Yes. Yeah. Okay. So for example, if we do not consider the dynamic input there, then if we have the fixed size of the input, then our operator fusion technique can be applied directly to the vision transformer. However, because input size is changed, that will give us some new opportunities. Yeah, we are exploring a more advanced, more optimized, version of the operator fusion for this kind of models. Yeah. Thank you.
Thank you. And my next question is that, so here you listed the CPU and GPU, that the mobile CPU and GPU, right?
Yes, you're right. Yeah, these are the mobile and CPU GPUs. Yeah.
So I was wondering, so how about the performance on the the desktop, the standalone CPU and GPU?
Yeah. For example, NVIDIA GPU and Intel CPU. Yeah. This is this is a great question. Actually, on the large GPU and usually, we run multiple models. Yeah, we not only run one model. Otherwise, we are going to waste the large GPU resource. So we can still use this. I believe this operator fusion technique and compression and compilation co-design technique still help the execution on this large GPUs. However, I think the more important issue is how to coordinate multiple models on these large GPUs. This is for the inference. Yeah, for training, that's another story. For the inference, I think the model co-run issue probably is more important on large GPUs. And we are also doing some, we are also having some ongoing work to handle this kind of issue. And of course, our techniques can be used for the large GPUs, but I mean, we haven't tested the performance gains or the effect of these optimizations. And another issue for the large GPU and the CPU actually is, I mean, for example, NVIDIA, for NVIDIA GPU, they have a highly optimized library like TensorRT. And so yeah. I mean, in that library, they need to use Tensor Core. Yeah. So I mean, probably this kind of new hardware features are also very important for us to improve the DNN execution on these kind of architectures. So I mean, yeah, as I mentioned, although our techniques are very helpful to apply to these kind of architectures, we have many new problems if you want to optimize the performance of DNN execution on these kind of new architectures.
So then on the other side, so have you ever like to evaluate your approach on those the even smaller CPU for those the embedded like the ARM A series CPU?
Yeah, this is a good question. We do. We evaluate on, we evaluate on the MCU, yeah, micro controller, and we can also get very good performance, and especially comparing to the microcontroller version of the TensorFlow Lite, we can get around 1.6 or 1.8 times speed up. However, on this kind of microcontrollers, actually the quantization is more important. Yeah, quantization is very important, and the memory management is very important, because for this microcontroller, the memory size is very small. It's very limited. As far as the on-chip memory size is very limited. And we also test on the Raspberry Pi. And actually, our techniques can be, migrated to Raspberry Pi very, conveniently, and we can achieve, also achieve good performance and Raspberry Pi, and we can also outperform other, execution, frameworks. Yes, yeah. To answer your question, yes. So we tried smaller devices, and also our techniques work well, and we can get performance gains.
So I was curious about it. So you just mentioned, so for those that like microcontroller, the quantization is more important. So why? Because since they are still not customer hardware, so they still have the kind of the requirement, like you cannot like have the 3-bit or the 5-bit. You can only have like the 4-bit or the 8-bit quantization. So then why quantization is so important, since you can also do the pruning there?
Yeah, the quantization is important because which can how to say? So based on my experience, for example, with the quantization, we can still leverage the SIMD computation efficiently. So for example, if we have 128-bit SIMD execution, then if we process if we process 32-bit integer numbers, we don't talk about floating point. If we process the 32-bit integer, then which means we can process 4 integers simultaneously. However, if we have very good quantization technique, we can't even quantize them into 8-bit integers. Then we can process, I think 16 integers simultaneously. We can significantly improve the parallelism. So yeah, that's why I say the quantization is also very important for the microcontrollers, because nowadays the microcontrollers have very nice SIMD support.
Okay, yeah. So that is based because the underlying reason because of the inherent CPU feature there, right?
Yes, you're right. Yeah.
Okay, I see.
Yeah.
So, any questions from the audience? So if you guys don't have any question, I will further ask.
Sure. Yeah. Go ahead.
Yeah. So I think very interesting. So in your second work, so the DNN fusion that, so you propose the graph writing, right?
Yeah.
So that very fundamental difference from the existing, those the fusion-based the optimization technique. And so I was wondering, so whether this philosophy can also be applied for the training phase.
Okay. I think so. Yeah, I think so. We can apply this kind of technique to the training to restructure to optimize the computational graph structure. Yeah, of course we can do that. Yeah. Yeah, this is not only limited to the yeah. I'm sorry. Yeah. Go ahead.
And for this graph writing, so it is kind of performed offline one time, or you need to be done every time.
This one is offline. Yeah, this one is offline, only one time, because we have the fixed, computational graph structure. Yeah. So in the training, if we are talking about, for example, we have a fixed computational graph structure, then we can apply this technique well. If you think, oh, during the training, I also want to adjust the, computational graph, the backbone, then probably this will, we need to design, more efficient way to perform this kind of graph rewriting. It's still possible, but we need to carefully control the graph rewriting cost.
So that means, for example, if the DNN topology it changes during the training, maybe this is not quite applicable, right?
This will incur some overhead. Yeah, but we still can define different kinds of techniques to control the overhead.
Oh, okay. Yeah. Okay, thank you.
Yeah.
Thank you very much.
Thank you.
So any questions from the audience? Okay, so if no more questions, so let's thank our speaker again. So thank you being so. I think there's one question from us.
Sure.
This is very interesting. As an undergrad student, how can I get involved?
Yeah, this is a great question. Actually, I'm working with some undergraduate students now, and the best way to get involved is start with a specific, DNN execution framework, and start with a concrete, demo. Yeah. So, for example, we can start with, the famous, TensorFlow Lite. We can, deploy this TensorFlow Lite on your cell phone. Yeah. On your Android phone. Even you can just deploy it on the simulator. And then, in this, framework, I think, it also provides some, very nice, demo or tutorials. And with these demos, you can build these DNNs at first and try to use these DNNs to inference some, data set to see some result. So this is a very good, starting point. And after this, you are going to get more, concrete feeling about the DNN execution, and also, the design and the implementation of these kind of frameworks, and then we can discuss more advanced research topics. Yeah. So I think this is this will be the recommended steps. Yeah. I usually use these steps to train my undergraduate students. Yeah.
By the way, being so follow up this student's question, I was wondering, because here our department is EC department, and we know that for compiler stuff, that is very hardcore computer science. So can you give our students some suggestions that, so which computer science course, if they are interested in the topic, so which they need to take, like some compiler course or any other courses?
Yeah, compiler and programming language course, and if possible, and also take some, graduate level, compiler course. I believe, if you want to systematically learn this compiler technique, then probably can, read some textbooks like the Dragon book or
Dragon book.
Very classic textbooks. And I believe there are also many, great online course videos, from different kinds of sources.
Okay, thank you. I think another audience asked a specific technical question. Count loop fusion technique covers this kind of work in the level of the LLVM IR?
Yeah, this is a great question. This is a great question. So, I mean, actually, I mean, if you take a look at our, DNN compiler, then you can see actually we have the front end and the back end. In the front end, we have this kind of, compiler on the computational graph. Yeah, the computational graph serves as an intermediate representation for the front end. So the machine learning compiler side. And after that, I mean, we need to rely on the LLVM, infrastructure and LLVM to generate the code and to optimize the code to generate the code. So I mean, essentially, the compiler optimization techniques presented in this talk is on the computational graph level. Is within the context of the machine learning compiler. It's not on the LLVM level. Yeah, it's not on the native compiler level. Yeah, but we do need to leverage the LLVM compiler to generate the code at the end.
Okay, in short, so that means that the approach you present in this talk, actually that is more on kind of the front end, right?
Yes, all right.
Yeah. Yeah. So then actually this question actually inspired me for another question. So we know that like for the back end or the middle end, we have like the LLVM, we have like the loop fusion, like using like based on the polyhedral model, blah.
Yeah.
This is a very rough thought. So whether you have ever considered to integrate your current front-end approach with the consideration of the back-end or the mid-end compiler technique together, kind of the mag fusion here?
Yeah, this is a great question. Actually, as I mentioned, we need to leverage the backend LLVM to generate the code. And when we use the LLVM generate the backend execution code, actually we do need to use the polyhedral-based loop fusion and loop optimization techniques in LLVM. The result here actually is already a combined result. Yeah, combined result. And actually, if you take a look at TVM and especially TVM, it also leverages LLVM backend. Especially it leverage a polyhedral-based highlight optimization to optimize its tensor tensor representation, and then leverage the LLVM optimizations to generate the optimized code. So actually for all of these frameworks, if you use the LLVM compiler to compile the generate code out to generate the code, then we have to use the LLVM optimizations. Yeah. So you mentioned a very interesting question here. Can we design specific techniques based on the polyhedral and combine this specific optimization with our current, for example, operator fusion technique? This is still possible. Yeah, this is still possible. We need to carefully take a look at the, for example, our generated code, and we double check if the LLVM analysis still apply for this code, and if there is any new opportunities. Yeah, this will be a very interesting research in the future. Yeah.
Yeah. So what I'm thinking that like we can propose some like the polyhedral aware, like graph writing approach. Not just simply use that as a concatenation, but it's kind of a deep integration together.
I see. Yeah, this is another direction. This is even more interesting. Yeah. So how to fuse the operators to facilitate subsequent polyhedral analysis. Yeah. This is very interesting. Yeah, this is very interesting. Yeah, I think it's a potential future research. Yeah. We need to do further more detailed analysis on these operators, on the features of these operators, on the features of the potential fused operators, and to see if after any operation, after any operator fusions, if it will disable some further polyhedral-based analysis and optimization, then we should discourage such kind of fusion. Yeah. This is very interesting. Yeah.
Okay, again, so thank you, thank you so much for this very informative talk. I really learned a
Thank you so
lot.
much for the invitation. Yeah, thank you so much.
Okay, thank you. Also, thank you everyone for attending our this week's talk. So see you next week. Thank you. Bye.
Yeah, thank you. Bye-bye. Yeah.